So with the RCPEK, it comes with this evaluation kit workbook, which gives you example models that you can build yourself, and it gives step-by-step instructions. You can start with a blank model and work up from there. But I thought I would go ahead and show one of the, this is the self-test model. The models in the workbook are build up to this basically. So you start out by just simply blinking a light, and this model is kind of the culmination of everything. So it kind of shows everything. Let's just start taking a quick look around at what's in here. This block at the upper left is the target definition block, and if I double click on that, you can see that's where you actually pick the target hardware, the 9064, the bit file package path, and the IP address, and you can even test the IP connection. I've gone ahead and connected up the Ethernet cable, and so we can test the connection to the actual Cerio chassis here. If it's correct, it comes back with the serial number. These options here give you the ability to either automatically load on power up, so each time you power cycle, it will load and run the binary. And the auto deploy function means that after the build is complete, it will automatically deploy it straight onto the hardware. So we want those options, and we'll just go ahead and hit OK. Some of the other blocks here are specifically for CAN, which you can go through the workbook and learn more about how that works. But essentially, you can load in the CAN database, and then everywhere you do a CAN read or write, it deals with engineering units. You don't have to worry about message bytes and bits. It takes care of all that for you. We did drop a XCP handler block, which allows you to do runtime calibration. And again, I won't explain too much about that, but you can look into that in using the workbook. And here we have a periodic task, which is set up to run at 100 hertz, and so everything inside this function block will execute at the 10 millisecond rate. Then over here we have a couple of other blocks. This is for triggering on IRQs, so it takes care of all of that. So each time we get an interrupt, in this case they're set up to run at top dead center of each cylinder. The interrupt processing is taken care of here, where each interrupt does a specific function for that IRQ. So if I navigate back up, then there are some initialization tasks which happen at startup. So we use a startup trigger block, and in this case it's only to set the port pin direction to define inputs or outputs. So if we look into the periodic task, you see where all of the, a lot of the real work is being done. For the most part, all of our sensors come in on the left. Here we're reading pedal sensor, engine speed sensor, throttle sensor, and key sensor. We determine what to do in the middle, and the outputs are all controlled on the far right. In this case, we are controlling mainly the electronic throttle control, so that's why everything's ETC. And the primary thing we're controlling is the throttle period and pulse width on the throttle control H-bridge motor. So if we go ahead and look at what's running in this, if I turn the key on, you'll see that if I move the load slider, which is this slider here, it actually simulates engine speed. So if I move this up, you see at each one of those interrupts, it turns a light on and turns the other lights off. So at each IRQ, it's simulating a cylinder injector firing or a spark plug firing. And you can see the tachometer is indicating the engine speed. And we even have a speaker so you can hear each time it hits DO0, it makes a pop on the speaker, so you can hear kind of as the engine speed goes up and down. That's 6,000 RPM, and I'll bring that down to some reasonable speed. Right now this is a open loop model. We do have a closed loop model. In the open loop model, you just set the speed and it holds that speed. The closed loop model would actually feedback based on how much fueling is put in. That would determine speed. So also in this model we have the throttle control, which is controlled by this APP slider. And as you can see, the throttle body actually is controlled by this. So the position of the throttle valve opens and closes as I move this up and down. And you can hear it as well. In the self-test model, we are also sending CAN message for the throttle. So one of the tests is if I flip this second switch here, it actually stops sending, well, that's the wrong one. Helps if I do the right one. Oh, here we go. So it's the first switch. If I had my workbook open, it would have told me that. The first switch turns off the throttle, and so you can kind of check that the switch actually works and does what it's supposed to do. So it basically ignores the APP position. If we run the engine speed, the other switches can be used to either turn all the lights off or turn all the lights fully on. So you can kind of check switch position, switch operation with that. And of course, if you want to, you can add on your own sensors and actuators as much as you want using these terminal blocks. So we have 8 analog inputs, 8 analog outputs, a total of 8 DIO pins, which can be used as inputs or outputs. And then we also have 4 digital inputs, which are really configured to use like a Hall effect or VR type speed sensors. Those also have the capability of triggering an interrupt. So we have a lot of hardware you can work with straight out of the box, or you can add your own sensors and actuators, and the sky's the limit.